Yeah, my name is Fitsum from Marwadi University. Today, I'm going to present you our research paper titled with utilizing inverted residual block in deep learning model for acute lymphocytic leukemia classification. So this is an effort of collaboration work with my co-authors, Kokou Elvis, Tete Winner, Reshma Sunil, and our guide, Anjali Diwan. And yeah, okay, here is how I organize the PPT. I start with the introduction and objective, then I'll walk through the methodology and our result, and end with our conclusion and future work. And okay, yeah, acute lymphocytic leukemia is also called acute lymphoblastic leukemia. It is a kind of blood cancer, which is actually caused by the immature growth of white blood cell inside the bone marrow. So as the name suggests, this ALL, it grows like rapidly. So within a short period of time, if you don't treat it well, it will get more worse, and it might be severe for all age cases. So actually, it's commonly occurs on children's, and it also happens on adults. But most of the time, it's generally it's occur for on children. Uh, where so these days, as we know, on medical images, machine learning and deep learning are performing well by analyzing the medical images for other types of images. We can we can easily detect and classify the stage of the stage of this leukemia. So there are different research on that, like this area ML and ML and deep learning has given to improvise like the to high performance. Besides that, also it's enhanced the diagnosis system by reducing the time and other effects. So yeah, as I mentioned earlier, like uh, this ALL, it gets worse or it gets severe in time. So early detection is necessary. It's crucial. So we experiment with different models, with different pre-trained models, and we create also our customized model. So our target was to optimize to get high accuracy with a small size of model. So our customized model achieve an accuracy of 98.5% and with a high amount of recall like performance. So yeah, we are okay. Yeah. So we go through different research workers like which are uh, focused on this area, acute lymphocytic leukemia. So there are different research papers. For example, Anil Kumar and his teams used AlexNet, which is a customized model. So they achieved around 94.14% of accuracy. And similarly, Jawar and his colleagues, they developed ALNet, which is actually developed on VG16. Yeah. So they achieved an accuracy of 91% and high F1 score. Not only deep learning, also machine learning also is performing in this area, especially in detecting different kinds of cancer and especially in leukemia. So there are multiple workers which achieve high accuracy and high performance. So both methods, machine learning and deep learning, they help for like for early detection. Beside that, and to improvise or to create a tool which is actually improve medical the medical system, especially it will help for the professionals in that area. So yeah, as any machine learning problem, we start from gathering the data set. So we get our data set from the open source Kaggle platform. So our data set, it was around 3,250 plus. So we divided for training, test, and validation sets. So as you see, for 70% of training and 30% we randomly divided to test and validation. So and there is a bit like the distribution is a bit not like, it's not same in all classes, but in our result, it doesn't affect. So we didn't apply any like balancing between the classes. So yeah, this is the process we apply. So we start from pre-processing the data set, because like the first thing we did is like we changed the images to the same size, which is standard to 256 by 256, which is standard for most of pre-trained model. And the pre-trained model, we used the VGG16 and Inception. So for our customizers also, we used the same size of like the same 256 by 256. And we changed the all images. The form of the image was, it was RGB. So we changed those images to grayscale image. It will fasten our training, and it will help the model to be like the value to be in the same range. So after this the reason why we select VGG is like the VGG16, it's performing kind of well in detection of different cancer, especially in acute lymphocytic leukemia. So VGG16, it is like, it has a power to extract information from these medical images or microscopic images. Same way InceptionNet, like the difference is that like in VGG, we use like the same size of filter. InceptionNet, it uses different size of filters, like 1 by 1, 3 by 3, and a 5 by 5 filter. So it has like using these different size of filters, like when it is 1 by 1, it will enable to extract information in small size of space or in a small part of the image. When it's big or 5 by 5 filter, it can recognize or it can extract the information like shape or in the bigger images. So yeah, our customized model architecture, it look like this. And the motivation we get, it is from MobileNet V2. It uses like, if you are worried about MobileNet, most of the time MobileNet, it perform well for like perform with the small size. So we look for what is the reason behind for MobileNet V2 to have such kind of performance with a small size of with a small size. So it will help for fast inference and for fast training. So in MobileNet V2, they introduce one of the block called like inverse residual block. So we use that one inside our customized model. So we use the 4 layer of this inverse residual block. So how this one works, like it has by itself, it has different like 3 convolution layers. The first one is 1 by 1 layer, the convolution layer. It will help to expand the channel of the image. So like when we give the image, the image will have like multiple channels. Then it will pass by the deep-wise convolution layer. So this deep-wise convolution layer, it will like extract for like it calculate for each layers. I mean for each channels. So the model, it can detect like or can easily extract the features from the image or from the input information. So the last 1 by 1 layer, also the convolution layer, it will help to reduce the size to one dimension. So this is how we structure. Then we reduce the size. Actually, like you might ask why we don't directly use MobileNet, because MobileNet, it has like around 53 layers, and it has around 17 layer of convolution inverted residual block. So like for our model, we just use four layer of inverted residual model, and other like just another additional 5 layer convolutional layer. So we try to reduce the size of the model. So yeah, after we train with after we train is all these three difference, so we analyze the result. So okay, so yeah, when we analyze the result, our customized model, it's performed over other pre-trained models. So we got accuracy of the blue line is for the VGG60. So we get accuracy around 95.3. And for Inception, we get accuracy of around 95.6. And okay, this is the line. For VGG, we get around 90. 96.2, and for inception rate, we get around 96.5, and for our customized model, we get accuracy of 98.55 accuracy. So, and as we know, like for medical case is, we don't just like, accuracy doesn't give us full information. So we look for another parameters, which is called recall. So because in medical, losing the positive samples, it is dangerous. So that's why we use recall. So which actually measure our prediction, or our prediction, like our model is perfectly catching the positive sample. So that's why we consider recall. And in this case also, our customized model perform over as a transfer learning model. So yeah, our customized model for recall of for the benign or for the normal, it is 96%. But we focus on, when it's recall, we focus on the positive classes. Like we have different stages, like from early pre-B, pre-B, and pro-B. So for early pre-B, like our customized model, it's achieve around like 96 point, it's more than 96. Actually, three of the model, they have the same amount of like catching the early pre-B. But for recall of pre-B and for pro-B, our customized model, it achieve 100% of recall. So yeah, this is our finding. Okay, well, yeah, acute lymphocytic leukemia, it is like one of the treated illness, like in children or in different age groups. So if you detect it earlier, like we have a high chance of treatment. So we are focusing on early detection of different stage of the early detection of this acute lymphocytic leukemia. And our model, yeah, as based on our experiment, we achieve like outperforming 98.5%, 855 accuracy, and our recall rate also, it is high. So in the future, we plan to reduce also the size of the model, and to improve the our performance also, not just the accuracy, our recall rate in different classes. And besides this, like now we are just working on cell type B. So acute ALL also has for cell T-type also. So we try to like diverse our data set, not only for this type B, I mean cell B, or also we are planning to include cell type T. So these are our future plan. So yeah, these are some of our reference that we use for our research work. Yeah, thank you so much.